Hello everyone, I hope you have seen all the videos that I made you. So let's start with the presentation. Short-term effects by Ashish White, Sagar Parsa, Nilesh Markade and Suraj Mere. Let's have a quick overview of what we are gonna learn. In this PPT, we'll be learning uh, what are short channels, what are short channel effects, then drain-induced barrier loading, surface scattering, hot electron effects, impact ionization, velocity saturation, which are nothing but the short channel effects only. We'll be seeing those effects in a detail. And first we have some prerequisite. Uh, Before we start up, you should know this all terms. Uh, Threshold voltage. It's a minimum voltage uh, that we give across gate and source, which allows the current to flow through the transistor. Then we have a subthreshold current, the current flowing through the transistor before the threshold voltage. Here the term itself says the definition, subthreshold current, the current flowing before the threshold, that is called as subthreshold current. Then pinch off voltage. Before we go with pinch off voltage, let me show you one diagram. In this, as you can see, the channel length is been modulated, and this total length we call it as effective length, whereas the actual length of the channel is this much, but the effective length is only this much. The voltage at which this effective length cannot be reduced furthermore. That voltage is called as the pinch off voltage. So we are done with the prerequisite. Now let's start. What is short channel? What do we exactly mean by short channel? Here we have two figures, long channel devices and short channel devices. In long channel devices, the channel length is so bigger that in long channel devices, channel length is very large than the width of this depletion width of the source and the drain. Whereas in short channel devices, the length has been shortened so much that the depletion width of the source and drain are very bigger than the length, the channel length. So the device in which the channel length is approximately equal to the depletion width of the source and the drain, or the channel length is very less than the depletion width of the source and drain, is called as short channel device. Now let's see what are the short channel effects. First of all, what do we gain by shrinking the whole device? The short channel MOS has good processing speed. As the channel length is being reduced, it shows a good processing speed, and it requires a low operating potential. How? That we'll see later on. And increases transistor density on the chip. Of course, if the whole device is being shrunk, you can fit more and more FETs on the same chip, on the same area. Although so many advantages, there are some significant disadvantages that the scaling process shows us. There are few performance degradation that we see while scaling down the device. Serious issues like DIBL, drain-induced barrier loading, surface scattering, then velocity saturation, impact ionization, and hot electron effect. Don't worry, we'll be seeing each one of them one by one. Don't get afraid with the names. They're too scary. Drain induced barrier loading. Just cut down this full title into the small words. Drain. Drain is a part of our device, that is source and drain. So that drain induce something happening because of that drain. Barrier loading. Now what do we mean by barrier? Barrier is a kind of wall which is avoiding or which is blocking the flow. So what do we have in our device which is blocking the flow? Nothing but our gate. The gate is made at such a height that the electron from the source can't flow and can't go to the drain part. The gate is been made at such a potential that the source can't go directly to the drain. For the electron to move from source to drain, we have to reduce this gate barrier so that the source can easily move to the drain. As in NMOS, we increase the gate voltage in the positive way, and we get this curve. Then if we increase it again, we get this curve. So the channel is being made from the source to drain, and the current starts flowing. In long channel, if the drain is made at 10 millivolt, we get this graph, and if we increase it furthermore, let's say at 1 volt, we get this graph. As you can see, significantly there is a difference between these two graphs. Earlier the slope was starting here, now it is starting earlier, but the barrier height is same in both cases. Whereas in short channel, the barrier height is as well reduced with the slope starting point. So what exactly happening is, your drain is controlling your barrier. It's a totally unwanted result. So the gate loses the control of flow of current through MOS and becomes as good as redundant. So if your drain only is controlling your device, what the hell the gate is doing? The gate is doing nothing. So here we have ID versus VG graph, where ID is in logarithmic form. Let me explain you this graph. Let me cut this down in parts. Here, this part is called the offset, where the VG is the below threshold, and this is the threshold point, after which it starts going up, and this is a transition part, and we have the on state current here. So I'm continuing the same example of drain 10 millivolt and then 1 volt. When drain is at 10 millivolt, we get this graph, and when we increase it to 1 volt, we get this graph, which is similar to the earlier one. Only the difference is the shift is been made. The upward shift is been made. The upward shift is nothing but an increase in the ID. So here in the offset, the current is being increased, and in the on state as well, it is increased by the same amount, and here the slope is the same. Whereas in the short channel, when the VD at 10 millivolt is same as that of here, but when it is increased to 1 volt, we see a slight increase in the ID, as we had seen here as well. But the remaining stuff, the slope and the offset current, are being changed now. The offset current is being increased by a very significant value, and it's not equal to the on current shift. Also the slope is being increased. This slope is called a subthreshold slope, and it is measured by x upon y. We usually measure the slope by dy upon dx, but here it is opposite. We take it dx by dy. So this is the increase in the slope, and this is lesser, and this is larger slope. So the slope has been increased, and as the slope increases, the threshold is been shifted to the left side or the right side of the plane, which is totally the unwanted phenomena. Yeah, as I had told you earlier, the short channel devices reduces our threshold point or threshold voltage, and it has been clear from this graph. The more and more we increase the drain, this subthreshold slope gets increased more and more, and the threshold voltage point is being shifted more and more, which again the unwanted phenomenon. And here we go with the surface scattering effect now. As everyone knows, FETs are the field effect transistors. These are the transistors which work on fields. Where exactly the field is in this device. EX is the vertical field generated because of the VGS, and EY is the electric field generated by VDS. For now, let's ignore this EY and let's concentrate with EX only. Okay, so in the long channel, this EY is actually negligible, so we do the calculation with EX only. And as the source and drain comes closer to each other, that is in short channel, this EY starts getting into the picture, and EY is no more negligible now. So there are two fields in one device which are active. One is EX and another is EY. So because of these two fields, the effective field is actually cross to this, as we can see here. So the electron goes here, bounces back, then again bounces, then bounces, and it goes like this, zigzag path, which causes it to reduce its mobility. No, the current is dq by dt. So if the electron or carrier is moving, so the carrier is moving straight from source to drain, it covers the distance. It covers the same distance in the minimum time, and if it is going in a zigzag path, it takes a larger time. So larger time, reducing the current. So ID has been reduced. Again, an unwanted phenomena. Same stuff is written here. You can refer the notes. I have made a link of my PPT below in the comment. You can check it out. Then we have a hot electron effect. Yeah. As I told you, now in short channel, the electron moves in a zigzag path, zigzag, and in a zigzag path like this, and at some point it goes up. Now why it goes up? Now assume that your drain and source both are at maximum higher potential. So you have a pinch off created, and because of the pinch off, the carrier gets a lot of energy. Really? And this energy gained carrier is called as hot carrier, as it has some excessive energy. So when it goes here while moving in a zigzag path, somehow it gains so much energy so that it crosses this gate oxide, and it penetrates through this oxide and goes to the gate. So what exactly is happening? The current is going into the gate. So our actual ID is now been split up in two parts. Splitting up is nothing, and at the drain point we are getting a lesser current. So our ID is again been reduced in this case. But this phenomena is used in a different way with different perspective, and is being used very nicely. The device, floating gate device, they have used this phenomena. What they have done is they have made a floating gate. That means the device with the two gates, one external gate that normally we have, and one floating gate. Now they purposely made few hot carriers within the device, and they catch up those carriers into their floating gate. As you can check out its working. I just told you the technique they use in the floating gate, and how to reduce this hot electron effect. You can easily reduce this by light doping of your drain. If your drain is lightly doped, this EY will certainly be reduced, and if EY is reduced, there will be only one electric field in the device, that is EX. So it would be as good as there is no EY and only EX in the picture. So somehow it will reduce your this hot electron effect. And then we have impact ionization. Electron flowing in a channel hits molecule, not the electron. So electron hitting a molecule, suppose if the molecule having some free electrons around it, this primary electron will hit that molecule and release the electron which was within the molecule before, and it will take away that secondary electron with it towards the drain. So now our ID is been increased, and because the molecule uses one of its electron, now it has deficiency of electron, and deficiency of electron is nothing but holes. Holes move towards the substrate, and this holes moving to the substrate cause latch-up, and latch-up is of course an unwanted phenomenon. I hope you are aware of the latch-up. There are two transistors, two BJTs created within the devices, and they suck a lot of current to the device such that the device gets burned down. And we have as we saw, it increases the ID current. The electron being sucked in the drain, the ID is actually been increased in the saturation region. Then at the end we have the velocity saturation. Here velocity up to the certain extent point, this velocity starts becoming constant. No matter how you increase your electric field, it will always remain constant. So the velocity loses its proportionality with the electric field. So here we end up with all short channel effects. Thank you for watching this video.